Hello, everyone. We're finally getting to real reactive systems, and that we're going to take what we learned over the last two lectures about thermodynamics and kinetics and put them into a real application by talking about real reactors. So, one of the big things that we're going to be trying to do is figuring out how we can set up a chemical reaction and what sort of control factors I can have to try and optimize how I run my reactions. Now, in order to do this, let's go ahead and look at a real chemical reactive system. And me being me, I like to take a look at one of the oldest chemical reactions that man has ever learned how to do: fermentation. So, basic idea of fermentation is I take sugar, I add yeast, I produce ethanol, CO2, little bit of heat, watch out for this one, and some more yeast, usually dead. So at this point, yeast is essentially acting as my catalyst. Here's my precursor, here's my product. Watch out because it will degas, so you have to make sure that you allow for buildup of pressure, and we have to find something to deal with heat. So if I want to go ahead and run a nice fermentation reaction, let's go ahead and start with the simplest approach. Maybe not the best, but definitely the simplest. Well, for that, we just throw it in a barrel. Barrel, pot, preferably something that, that keeps the system anoxic and prevents the entry of oxygen. The classic choice here is a barrel. So a barrel is essentially the simplest form of a batch reactor. So the idea of a batch reactor is I throw all of my reactants and my catalyst into one container, let it sit, pull it out when the reaction is done. So at the end of reaction, I've got a nice little solution. I go ahead and I purify that, whether that's via distillation or simple filtration if all I'm aiming for is pulling out the unreacted starting material and my catalyst. Now, turns out this type of method has a lot of shortcomings, but in order to look at this, let's try and walk through them one by one. So, especially as I tend to scale up this reaction, a lot of these problems will become much more apparent. So the first big problem is that my system tends to be very ill mixed. So I'm going to have my yeast tending to either go to the bottom as they essentially die, or tend to float towards the top. So I'm going to have a stratification of my reactants, especially because sugar tends to be a little heavier, yeast tends to be a little lighter. We don't want our catalyst separated from our reactant. So simplest option here, I add in a mixer and I add in some baffles. The mixer keeps everything moving. The baffles end up encouraging turbulent flow so that the whole system turns over. So this is essentially the simplest corrections we can make to the system. Now, especially as I scale up this system, so for small systems, the heat transfer out of the reactor will more or less handle itself. It's cool enough out here. It's not too warm it doesn't get too warm in here. And especially if I go to a metal exterior, the heat transfer is just fine. However, as I get bigger and bigger, I'm producing more and more heat, and my surface area just isn't increasing at the same rate. So for that case, we have to deal with this extra heat. And the typical answer here is I add in a cooling jacket. And you'll actually see this in a lot of industrial scale fermenters, is you're going to have some sort of cooling jacket to help increase this this loss of heat and keep my system from overheating and more or less killing my yeast. So then we have to worry about, well, I've got this extra CO2, and I tend to need to keep the oxygen out, so I tend to work with a sealed container. However, as I start scaling this up, I'm producing a little bit too much CO2. So either the CO2 ends up killing the system in here by driving the reaction inverse as I overpressurized it, or I ended up overpressurizing it and I rupture my batch reactor. Well, that ain't good. So in this case, if I have excess gas, we go ahead and add in a vent. So vents will help make sure that any gas flow is unidirectional, And this will make sure that I don't bring in any O2 or N2 from the atmosphere, but I prevent an overpressurization and I allow product release. Now, one of the other difficult problems we have is that, well, I'm going to need to add in, um, I'm going to want an easier way to add in my reactants and to pull out my products. So the typical easiest way to do this is we add in an input at the top and an outflow at the bottom, especially when you're dealing with liquids. This tends to be the easiest way to encourage smooth flow. So this is essentially the general shape and design of most of your classic batch reactors. And these tend to be the nice, cheap workhorses of most industrial chemistry. Now, we're going to went ahead and figure out what's going to be the rate of reaction in this system. So, rate of reaction is going to typically depend upon the concentration of, let's say, my limiting reagent, in this case is glucose. So it's going to be related to essentially the change in the glucose over time. So this tends to give us two ready controls over both the rate and essentially my product distribution. So I can either change the amount of concentration of my reactant, or I can change the amount of time. So let the reaction run longer. But one of the things we run into is that we're still going to have some limits over the possible conversion of my reactant to product, just simply based on thermodynamics. So at the beginning, we tend to have the fastest rates because I have the most amount of reactant. However, as time goes on, my rate's going to increasingly slow down. So I'll have a fast reaction rate at the beginning, but it takes longer and longer to get the same amount of conversion the further down I go. So one of the problems that we have is that it's not always going to be possible to allow infinite long residence times. So I need to find some sort of compromise of how long do I want to let the reaction go in order to get a certain amount of conversions. So one of the things that we can do to try and help speed up this problem so I don't have to run a reaction infinitely long to get the conversions I want is, instead of just adding in all of my reactants and products all in one, adding in all of my reactants in one go and pulling all of my products out at one go, we can take this same reactor and run it in a continuous form. So this is called a continuously stirred tank reactor. So the idea is I take this same high-tech batch reactor and I just keep pumping in my reactants at a steady rate. And I'm going to keep pumping out my products at a steady rate. In reality, you'll often run a CSTR, because that's the acronym we tend to use on this thing. Not quite so much continuously as maybe semi-continuously, where I'll say every day add in a new set of inputs and every day pull out a new set of outputs. However, the math to describe the system is a little bit more complicated. So let's work with the continuous or steady state form. But again, we can run this either steady state, constant flow and outflow, or a more unsteady state where I have more pulsed flow and outflow. Now, why would I go ahead and run this batch reactor in this more steady state fashion? So what's the advantages of running this continuous case? Well, one of the biggest advantages is that I'm going to see a certain amount of more predictability in my rate. Because if the concentration inside the system is at a steady rate, is at a steady concentration, I'm going to get a steady and, more importantly, predictable rate in and out. And this is going to give us a lot of real operational advantages. However, one of the things you have to watch out for is there's going to be a certain amount of precautions that we're going to have to take. Most notably while running the coolant and watching out for CO2 production. And again, the big thing is to make sure that we have a continuous stirring event and the whole thing is more or less homogeneous. If you don't have a good setup for the reactor, it's easy to get pockets of high concentration and low concentration. And the last thing you want is a pocket of low product concentration near the bottom or outflow, which is something you should watch out especially when dealing with different density products and reactants. So again, one of the general precautions we can make to avoid this ill mixing is that we want the residence time to be about 5 or 10 times longer than the mixing time. So the mixing time essentially could be modeled by, say, putting in dye and then figuring out how long it takes to make sure that the system is fully mixed. So you're going to want to make sure that everything has gone through the whole reactor about 5 or 10 times before it gets pulled out. This will also need to be modeled based on the reaction rate itself. So getting back to this reaction rate for our nice CSTR, in this case, the reaction rate of the system is going to be based entirely on the concentration of the system, which under a continuous model should remain fixed. And the reaction rate will also be based on the mean residence time. So essentially, the longer the mean residence time, the more complete the reaction we should end up ensuring. So again, the mean residence time can essentially be expressed as a ratio of the volume of the reactor versus the flow of the reactor. So if I have a large volume and a low flow, this means that that any chemicals entering the system stay here a long while. However, as these two things get relatively closer together, that means that it's essentially just a shear pipe that I'm pumping material straight through. And again, all of this is assuming steady state. So this gives us some information about mean residence time, but what about the concentration, the effective concentration of the system? Well, we end up running into a nice advantage here with CSTRs, because in order for the system to be well mixed, the concentration inside the reactor has to be the same as the concentration of the product exiting the reactor. And so we can use some mass balances to help describe the system. So essentially, what we can do is rely on the fact that the moles of reactant I'm feeding in have to be equal to the moles of the reactant coming out and the amount being consumed. So let's say I've got a first order reaction. So the rate of reaction is going to be given by the rate constant times the concentration of my reactant A. So in that case, what I can do is more or less plug in my values for the moles being added in. So the moles being added in is going to be based on the concentration of my input times the feed rate of my input, which I'm going to represent as the flow rate Ft. Now, if I'm running the system at steady state, the flow rate for my input should also be the same thing as the flow rate of my output. And the moles coming out should then be the moles of my reactant coming out should be the concentration of the reactant in the output times that steady feed rate. However, we also need to account for the amount being reacted, which will be based on our volume scaled rate of reaction. So in this case, I'm using a normalizing quantity of the volume of the system, which also happens to be our classic rate expression. So I can go ahead and substitute in my rate expression into this equation. And what we end up with is the moles of reactant coming in is going to be equal to our concentration of the reactant in my output times the rate constant times, again, the concentration of the reactant in my output, because that's the same thing as the concentration of the reactant in my system, times, again, the volume of the system. Now, what's actually quite nice about this is that we can actually use this equation to figure out what the volume is of our reactor, because usually external mass balance considerations have dictated our feed rate, and external factors have dictated our conversion, the concentration of our reactant and are essentially conversion to give me the concentration of the output. So I can essentially figure out what volume of reactor will give me the concentration of the output that I require, as long as I know the rate constant. So let's go ahead, and since this is a little bit messy, work it for a real problem. So let's go ahead and take a look at the degradation of cumene hydroperoxide, which is a very useful precursor of phenol. So again, what we can do is look at the reaction of CHP to produce phenol with a side product of acetone. And it turns out that this reaction is pseudo first order, as it has a dependence upon catalyst, which is usually a catalytic initiator, which is usually present in excess. So if I want to go ahead and, so what I want to do is figure out how big of a reactor I need to achieve a certain percent conversion. So let's say I want to have an 85% conversion of my CHP. So this should give me, again, about an 85% yield. So I'm going to do this for a reactor where I have a feed rate of about 27 cubic meters per hour, and a rate constant of about 4.12 per hour, which again is going to be dictated by the nature of the reaction itself. So how can I go ahead and solve for the percent conversion, or for the volume that will drive this percent conversion? Well, in this case, we can make use of the fact that if I have an 85% conversion, it means that the concentration of CHP in my output is going to be 0.15 of whatever got added in. So from there, we more or less end up making use of our mass balance. So the moles in is already dictated, and now we're essentially making use of, this is the number of moles of CHP in my output, and here's going to be the number of moles of CHP that's consumed, again, in a per hour basis. So we can then go ahead and plug in our numbers and solve for the volume. And when we go ahead and do this, we find that we need a reactor of about 37 cubic meters. Or in other words, we need a reactor about a little under 4,000 liters. So we need quite a large reactor to help drive this percent conversion. Now, it is worth noting we are pumping in at a fairly large feed rate of about 30 cubic meters per hour. So this does indeed give us a residence time in the reactor of about a single hour, which isn't too bad. But let's be honest, getting a 4,000 liter reactor isn't exactly going to be the cheapest thing you've ever done. So what we might want to do is figure out if there's a way we can make a much smaller reactor. So one of the big things that's important to think about when we're figuring about controls on the rate is that the rate of our reaction is indeed going to be in large part dictated by the concentration at our outflow. So if I want to speed up the reaction, well, the answer is fairly straightforward. I can essentially reduce the residence time by increasing the concentration, by decreasing my yield. So what this means is that we can, say, split our single large reactor into two smaller reactors. The first reactor is going to run a lot faster because, say, it's going to have a concentration of our reactant that's much higher. So I may be able to run it through there faster, or I might just need a smaller reactor in order to run at steady state. And what ends up happening is that by increasing our number of reactors, what I can end up doing is drastically increase the rate of reaction in every single one of these reactors, except for the last one. So if I'm, say, running through 6 reactors, most of the reaction is actually taking place in this first one, a little bit more in the second, then a little bit less in the second, then a little bit less in the third. By the time we get to this 6th reactor, it's only converting 1 or 2 extra percent. But what this ends up doing is drastically decreasing the amount of volume or the size of the reactors that I need, though indeed you will need to purchase more individual reactors. So this does lead us to a question of how do you choose how many reactors you want to run in series? And this is often going to be dictated by cost. I might not be able to find the space or time to run one big 4,000 liter reactor, or if it would theoretically require something bigger, 4,000 is about as big of a reactor as you can cheaply buy. So in general, that's going to be one of the major considerations we have to take into account. But this actually leads us to a good question. In general, if I want to speed up my reactions, it turns out that more reactors is better. So this leads us to an interesting question. What's going to be the actual best way to set up a reaction? Turns out it might not actually be having all of these individual reactors. It may end up being having a big long pipe. So next time, we're going to be taking this concept to its logical conclusion by looking at flow-through reactors. Till then, take care.